all. This is Mr. G, and this is our warm-up for today's lesson. So pause the video right here, give this problem a shot, come back when you think you have an answer. We're going over 3, 2, 1, let's go. The warm-up says we have to solve the equation 0 equals the absolute value x minus 5 plus 2 times the square root of x minus x. What an absolute nightmare. I mean, I'm sure it might be possible to solve this by hand, but I wouldn't even know how to start. I would really have to think for a while to come up with a strategy to try and solve this by hand. But fortunately, we've got a graphing calculator we can use. And to solve something with a graphing calculator, we just rewrite the 0 as a y. We turn it into a function, and then we find the real roots. Hopefully we remember from our last video. The real roots of a function are the same thing, or how do I want to say this? The real roots of a function help us find the real solutions to the equation it matches. So I'm going to turn my calculator on, hit y equals. So we want absolute value, so I have to hit math, go over to number for the absolute value. Oh, why didn't I hit y equals? There we go. So math, go to number, absolute value, x minus 5, hit right to get out of the absolute value, plus 2 times the square root. I have to hit second, x squared gives me a square root. X, hit right to get out of the radical, minus x, and now we're ready to graph. Let's see what this looks like. All right, sort of a weird looking function. I've never seen one that looks like that, but we don't care about the function. Remember, the only reason we graphed this was to find the real roots, and we can see it looks like there's 2, if I can sort of draw an approximation, because I can't really draw on the graphing calculator, at least not well. It looks like it's going down here, then back up. So we're going to have one real root. Let me do this in a different color. One real root right there, and one real root right there. It's our job to find it. So I hit second, calculate, go to 0, which is number 2. Then we have to do the left bound, right bound. So this point right there is to the left of my first real root. I hit enter. Then we go to the right. I've passed it there. I hit enter. Enter one more time. Come on. There we go. And the first 0 at this point is 4.66 we'll round to. 4.66 and 0. The second one, we go second, calculate 0. Do the same thing. Right there should be to the left of that real root. Hit enter. Now I move right. I think I'm past it, but I'm going to go a little bit farther just to be sure. There we go. Hit enter. Enter one more time because we don't care about guessing. And we get the 0.6, 0.25, and 0. So those are the 2 real roots. But remember, even though we're using the real roots, it didn't ask us for the real roots. It asked us to solve the equation. It asked us to find the solutions. So the solutions aren't going to be an ordered pair. They're not going to be an x and a y. There was no y in our original equation. So we're just going to say, okay, x equals, the first x value we had was 4.66. I guess that should be an approximate because we rounded. And the second one we got was approximately, actually no, that's not approximate, that's exactly 6.25. And those are our 2 answers to this solution. Those are the real solutions at least. Let's take a look at our objective. Today we're doing chapter 4, section 3. After today we should be able to find the local extrema of functions. Now right now if you're thinking, what does that word mean? That's okay. That's one of the first things we're going to talk about. Let's jump to our vocab. So we basically have extrema and we have local extrema. Now, whether or not you know, whether or not you've heard those words before, let me turn this off just so it's not in my face distracting me. Whether or not you've heard the word extrema before, you actually have already done at least some work with extrema because all extrema means are maximum or minimum values. And hopefully we know what the maximum is. That's the highest point in a graph. And the minimum is the lowest point in a graph. So whenever we're talking about maximums or minimums in a graph, we're actually talking about extrema. That's what the word extrema means. It just sort of encompasses both. So if we're ever asked to find the extrema of a function, that could be the maximum values or the minimum values. Right? So just keep that in mind. Now local extrema, so it's the same thing extrema, but now we're talking local extrema. Well, if we think about what the word local means, like if we think, okay, in a local area, that's in one sort of section or one closed off, maybe not closed off, but one area. So not the whole graph, but maybe a smaller section of it. And that's exactly what a relative maximum is. So go a little bit further. It's the highest point in one section of a graph. And the relative minimum is the lowest point in one section of a graph. So one function might have multiple relative maximums, but it can only have one absolute maximum. Because there could be like, okay, this is a maximum in this local area, but if we look at the whole function, there's only ever going to be one maximum or no maximum at all. And the same thing goes for minimums. There could be multiple relative minimums, sort of local minimums, but for a function, there's only ever going to be one absolute minimum or none at all. All right, let's take a look at a few simple examples here. So we've got two parabolas drawn here, one with vertex A, one with vertex B. And the question is, what point is the maximum of its function? And that would be B. B is the maximum of its function because it's the absolute highest point on that graph. Then the next question is, what point is the minimum of its function? And hopefully we see that would be point A, because point A is the absolute lowest point of that function. Now let's take a look at this graph. So it says, what point is a relative maximum of the function? What point is a relative maximum? So we're not talking about a maximum here. We're talking about a relative maximum. Here we're looking for local extrema. Now, why is that? Why can't it just say, okay, which one of these points is the maximum? Does this function have a maximum? What a lot of students say is they say, okay, I bet I is the maximum because that's the highest point we see. But my response to that would be, well, is it actually the highest point we see? Because remember, this arrow means it's going to keep on going up. So like this point right there, that's higher than I. So we might think, oh, that's the maximum. But it's not, because no matter what point we pick, that arrow means it's going to keep on going up. There's always going to be a point that's higher than a point we pick. And similarly, over here, like any point we pick, there's always going to be a point lower than it, because that arrow means we're going down forever, infinitely. So that's why we're talking about relative maximum, local extrema. So now we're looking for a maximum in sort of one section of the graph. And it's still not I though, because if I look at that section around I is not a maximum. But there is a part of the graph where if I just focus on that one section, we get a maximum, and that's around point C. If I look at the local area around point C, we get a parabola, a concave down parabola. That means there is a maximum. So the relative maximum of this function is point C. Now we're looking for which point is a relative minimum of the function. So we do the same thing. We say, okay, so where do we see the opposite of what we just saw? So instead of a concave down parabola, we're looking for a concave up parabola, and we see that right there. If I just focus on this part of the graph, we see, oh, point F is a relative minimum. It's not the minimum of the entire function, but in this section right there, if we ignore the rest of the function and just focus around point F is a relative minimum. Now let's jump in and do some real examples. So example one, we have to find all local extrema of the function negative x squared plus 4x plus 3. I'm going to turn my calculator back on if it'll respond. There we go. Now we'll go to y equals to graph it. Y equals, there we go. Clear out that old function. So it's negative x squared plus 4x plus 3. I'm going to double check I typed that correctly. Negative x squared plus 4x plus 3. Good. And now we get graph. Waiting for it to graph. Okay, we have a concave down parabola. So the first question is there a relative minimum? Well, I don't see a relative minimum at all, so there's none. No relative minimums. There's none. Because those two parts of the parabola are going to keep on going down and down and down. So there's no relative minimum. I do see a relative maximum, though. That point right there. I need to trace just so I can show you where I'm looking. That point right there, again, I can't get exactly there by tracing, but that point right there is a relative maximum. In fact, it's an absolute maximum. It's not just a local extremum, it's a extremum itself. That's tough to say, extremum. So I forgot to talk about this earlier. Extrema is plural, that means more than one. If we're ever talking about just one extrema, then we would say it's an extremum. So let me write that out, just so you can see that, extremum. That's not like super critical to know. A lot of people just use the word extrema. But if I ever say extremum, just know I'm just talking about one of them. Okay, that was a little tangent we went on there. Okay, so we've identified there is a relative maximum, but how do we find it? There is a way to find it by hand, and we will go over that at some point. But, I mean, we've got a graph and calculator. Let's just do that. So hopefully we remember, okay, to find something on a graph, at least one place we can start is the calculate menu. I'm gonna hit second, calculate to get to the calculate menu. And then if we look, oh, we've got two options here. We've got a minimum or a maximum. So we're looking for a relative maximum here. So let's hit 4 to find a relative maximum. Now, it's going to ask us left bound, right bound, and it's going to ask us to guess. So essentially, the calculator is saying to us, okay, I'll find a maximum for you, but you have to tell me where to look. You have to give me something on the left and something on the right, and then I'll look in between them. So I need a point to the left of my maximum. I'm going to hit enter right there. Then I just have to make sure I pass the maximum for the right bound. So there would be okay, but we can even go a little bit farther. That's fine. Hit enter right there. And then when I hit enter one more time, the calculator is going to look in between those points and find the highest value of the function, at least the highest value in that section. Oh, we got, looks like 1.9 repeating 7. 1.9 repeating 7. But if you wrote this, I don't want to say this. If you're ever taking a test or a quiz or just trying to answer a question and you put anything 0.9 repeating, that's going to show that you don't entirely know what you're talking about. 0.9 repeating doesn't actually exist. That always gets, I was going to say rounded up, but that's not even the correct phrase to use. It's not rounded up to 2. 1.9 repeating is 2. That's the same exact thing. So another way to think of that is that anytime you see 0.9 repeating, that's equal to 1. It's the exact same thing. Explaining why that is sort of a tangent I don't want to go down right now. Just take my word for it. Anytime you see 0.9 repeating, just remember, oh, that's actually a 1, so I gotta, again, I'm going to use the phrase round it up, but I'm not even crazy about that phrase. I need a new phrase. We just have to remember that it equals 1 more than we see. So 1.9 repeating, that actually equals 2. All right, so there's our relative maximum, or excuse me, our maximum value, because that's the maximum of the entire function. Let's jump to example 2. Got to find all local extrema of the function f of x equals x to the third minus 3x plus 1. So I hit y equals, clear out the old function, and it's going to be x to the third. Now, to get to a power of 3, you need to hit the caret button, which is an arrow up like that. It looks like that, and you can see it just below the clear button. All right, that'll get you to an exponent. I'm going to type in 3. And now I don't want to keep typing. I have to hit right to get out of the power. And then I'm going to hit negative 3x plus 1. And we're going to graph it. And there we go. So I actually see a relative minimum and a relative maximum here because I see part of this graph looks like a concave up parabola and part of it looks like a concave down parabola. Let me sort of redraw this just so I can sort of show you what I'm looking at. As soon as I see this graph, I think, okay, there's a relative maximum right there, and there's a relative minimum. We're just looking for one part of the graph that looks like, okay, yeah, that part looks like a parabola, either concave up or concave down. That's what you look for to get a relative maximum or minimum. All right, so let's find the minimum first. So second, calculate. Minimum is number 3. And again, we go left bound, right bound. So that's to the left of my minimum. Then I hit right till I pass it. That's good enough. Enter. And one more time. We get the point 1.000008. So we'll just say that's a 1 and negative 1. So 1, negative 1 is a relative minimum for this function. Again, it's not an absolute minimum. It's only a relative minimum. If we look locally around that point, it's the minimum on the function. Again, in that local section. Now we need to find the relative maximum, so I'm going to hit second, calculate maximum is number 4, and I have to go to the left. So my maximum is right about there. I'm going to go to the left a couple clicks, hit enter. That was probably farther than I needed to go. Then I hit right till I pass the maximum. That looks good. Hit enter. Enter one more time, and it gives us a maximum value. A lot of weird decimals going on here. That's a negative 0.9 repeating. I know there's a 2 at the end of it, but there's a lot of 9s. So we'll say that's a negative 1. And the y value is a 3. A lot of weird things going on with the x values here. Yeah, sometimes the graphing calculator tries to be a little bit too specific and it ends up looking kind of stupid. Before we move to example 3, and I give you one to try on your own, I think it's on your own at least. Yeah, before I give you one to try on your own, there's something I want to talk about with the left bound, right bound that you need to be really careful about. If you're doing left bound, right bound, trying to find a real root, and you mess up the left and right bound, the calculator will tell you. The calculator will tell you, oh, you made a mistake. There's an error. I can't find the real root. But it won't do that for a maximum or minimum. And let me show you how it looks. So let's say I go to second, calculate maximum. And I'm trying to find the same relative maximum. So I'm going, okay, yeah, that's the left of it. I hit enter. Now for the write down, let's say I'm a student and I just go this far. That's not far enough. I did not pass the maximum. But if I hit enter and then guess one more time, the calculator gives me a maximum. It gives me an incorrect answer. Or not really an incorrect answer because we asked the calculator to look for something we actually didn't want to look for, or we asked it the wrong question. That's a better way to say it. Like what we just did, and again, let me draw this just so we can see it a little bit more clearly. What I just did there, how do I want to say this? When we do the left bound and right bound correctly, we're saying, okay, between these 2 points, find the maximum, and it does. But what I just did when I made this mistake, let me get rid of those, is I said, okay, look between those points. And the calculator looked in between them and said, okay, so the maximum is right there. So the calculator gave us a maximum for the area we wanted to look in, or we told it to look in, but it's not actually a relative maximum because we did not do our left bound, right bound correctly. So the moral of the story is, if you're going to use the maximum and minimum, be really careful with your left bound and right bound. And also, just look at the graph. Like if you look at the point that's blinking right there, I'm pointing at it like you can see it. If you look at the point that's blinking right now on the graphing calculator, you can see obviously that's not a maximum. That's not a relative maximum because it's right, it's about there. That's not the relative maximum. We were looking for that point. So when you're using your graphing calculator, make sure you're also using your brain. Don't just sort of, go to sleep and just mindlessly take whatever answer the calculator gives you. Okay. Last one for this video. I want you to try this one on your own. Come back in 3, 2, 1. Let's go over and see if you got the correct answer. We want to find all local extrema of the function f of x equals absolute value. So let me go get an absolute value. Math number, enter for absolute value. X squared minus 3. I have a feeling this is going to be a weird looking function because we've got a power inside an absolute value. Let's see what happens. Yep, that's a pretty weird function. But to find the relative maximum and minimums, we can just use the graphing calculator. So in case anyone just wants to check their answers, there they are. I got negative 1.730 and 1.730 for the relative minimums and 0.3 for the relative maximums. Now I'm going to take a couple minutes and just show you how I got those answers in case anyone wants to see how they got the answers. I go to second, calculate. Let's do the minimums first. I'm going to hit 3 for minimum. Let's find the one on the left. So that's to the left of the minimum. Hit enter. Pass the minimum. Now we're on the right. Hit enter again. Enter one more time. And we get negative 1.73. Oh, and we got that 7.5381 e negative 7. But remember, hopefully you remember from the previous videos when we talked about this. Anytime you see e and a negative when you're doing, it happens most often with real roots or maximum or minimums, but anytime you see that when you're working on a graph, that e followed by a negative, just remember that's a 0. The calculator is like giving us a really small number in scientific notation, but it's just a 0. All right, so that's one. Second, calculate minimum. Now we'll find the other one. Hit enter on the left of it. Move to the right of it. Hit enter again and enter one more time. And we get 1.732. We just rounded it. And again, we see some number, but we see an e negative. So I don't care if it's e negative 6 or e negative 12 or e negative 10, whatever it is. As soon as you see that e and a negative, you know it's just 0. Now for the maximum, second, calculate maximum is number 4. Scroll over to the left of my maximum, hit enter. Move to the right of it, hit enter. Enter one more time. And now we have an e negative 7 on the x. So again, that means the x is 0, and we get a y value of 3. So a lot of weird things going on with the graphing calculator as far as it like trying to round to too close of a number, but whatever. We know how to read this. All right, hopefully that all made sense. If you have questions, by all means, let me know. Enjoy the rest of your day.